So once again, welcome you all for the part 4 review of entropy in the second law of model number 1. So just I am going to continue with what in the part 3 we have completed what is first law and the second law of thermodynamics. So now in the further case, so just we are going to deal with what is entropy. Actually, basically entropy, this is a property of a system. Entropy is a property, it is a point function, it is not a path function. So these are proved by means of Clausius theorem, Clausius inequalities. So with that one we will come to know that entropy, it is a property of a system. So we will go in detail of these things, and then afterwards we will the next session it may be carried out for the different types of processes used in thermodynamics. So in the last 2 or 3 sessions we have covered what is first law and what is second law of thermodynamics. So in the first law we have studied that dq is equal to du plus that work done, that is dw. Okay, so here if du is equal to, this is pdv, so in case of this thing also I can write it as for a constant volume process. So for a constant volume process, if you take V is constant, so in this case pdv will be 0, right? So for a constant volume process, dq is equal to du, right, plus 0. And what is du? It is nothing but for a constant volume process Cv into dt, right? So substituting here, dq is equal to Cv into dt. So in that case we can write what is the definition of Cv, specific heat at constant value. So many times the students are not knowing this one. dq by, sorry, this is du is equal to this, both are equal, so hence here I can take du, right, equating both the things. So here I can write dq is equal to Cv into dt into du, right? So Cv is equal to du upon dt at constant value. So if I take temperature as this one and the internal energy on the ordinate, you can have this the constant volume process. So there is a specific heat at constant volume. So it is a rate of change of the internal energy with, it is just a ratio of internal energy to the temperature, difference of temperature at constant value. Okay, this is how we can prove that. So that means the specific heat at constant volume is derived with the first law of thermodynamics, right? So the other thing which is there, so in the, on the other hand, even we know that dq is equal to du plus pdv, right? And now one more property, just I want to write it as enthalpy. So whenever we say that the property, it is a point function, it is not a path function. Okay. So enthalpy is a property of a system. So enthalpy, we can write it as the sum of the internal energy and the flow work. Internal energy and the flow work. So here, this is this, since U is a property, so hence internal energy, H is a property of that. So P into V, it is now it is a flow work, but it is independently if we take pressure and this is a specific value. It's not a value. So in that case, it becomes H is equal to U plus V, that is kilojoule per kg, right? Because this everything we are taking per unit mass. So in that case, this we can write it as H is equal to U plus V. So now here, if I differentiate this term, if I differentiate this term, for that, for a diploma holders, you should know how to differentiate it. So applying the differentiation, dH is equal to du plus differentiation of the two variable pb, right? So dH is equal to du plus, so if two variables are there in that differentiation, you can take one is constant and other one you can differentiate, and the v is constant plus dp, right? So like this we can get it for dH. So here dH is equal to du plus pdv. Du plus pdv is what? Just now we have learnt. This is nothing but dq, right? As per the from the first law, plus vdp. So hence dq is equal to dH minus vdp, right? So this is the derived equation from using the enthalpy. Okay. So now in this, if P is constant, so in that case this way will be 0. So what you will get at a constant pressure, dq is equal to dH, right? And what is dH? It is nothing but the change in temperature at constant pressure, that is T2 minus T1 or delta T, the Cp into delta T. So hence I can write Cp is the ratio of change in heat transfer to the change in temperature at constant pressure. So this is the definition of specific heat, okay, at constant pressure. So try to remember these things, because these are the things we are using in the further in the equation of say the wherever that heat transfer is there, or else in the refrigeration and air conditioning, the applications of the second law of thermodynamics or air cycles, we are using this equation. So that's why I try to remember this. Okay. So now one more, that in the first law of thermodynamics, that energy, that is an integral of work, integration of work is equal to integration of, what is that? Heat. So this is, you have learned it. And further, after that is first law is applied to the internal energy. So that's why we have proved that dq is equal to du plus the work done, pdv. Okay. So that means it talks about the internal energy. First law it talks about the internal energy, right? So the other one, that is we cannot say that again energy conservation from the single source we cannot get always energy. If I am getting from one source without any input to this, if I am getting the output, so that is not at all possible. So this was this is says perpetual motion machine of first kind is not possible. Is not possible. So whereas in the second law, what we have taken is the other one, that is the perpetual motion PMM2 is not possible. That is, if a source is there, single source, it takes heat Q1 from this and it gives out the W1. From a single source, if a pump or anything, if it is taking heat and then giving out the work output, so that is also not possible, because that thing it is needed, a rejection of heat will be there. The two sources are required. This is called Kelvin Planck statement. Kelvin Planck statement. So this Kelvin Planck statement, it is very important to derive the equation of what you can say that temperature scale. The temperature in Kelvin is equal to 0 degrees Celsius plus 273.16 Kelvin. So this is, it is taken by applying a series of reversible Carnot engines. Reversible Carnot engines. So try to study it very, because that gives you, if you apply a series of Carnot cycle. So what is a Carnot engine? It takes the heat, right, and it gives out the work. Let us say this is T1. Sorry, this is T1, and here I will take Q1, and this is Q2. Okay, and this is the rejection. It is say T2. Here what we will get is W. Say W1. So similarly, if I apply in this one, if I apply this T1 and T2 are some of the things. So here, if I apply the number of engines, so this is T2, T3, and here you will get W2. So again, from the T3, I will take, this is the source, this is the source, here you will get, this is Q2, Q3, right? And this is T3. And now T3 is a source. You can take some heat from this, and then so rejection will be there. So you try to n number of series if you apply it in between the two sources. One source is this and the other source. This is the source where T1 is there, where this is the last source where T2 or Tk is the last source in that case. So if you go for a number of uh, sources like this, 3, 4, 5 Carnot engines, if you apply it. So finally, here there's one possibility you will get always Q, whatever you are rejecting, it will go on reducing, isn't it? So that means it may equal to 0. So that is not possible. We should not go for that thing. That means always it must be a finite. If there is a finite, then only the engine will work. Otherwise, it is just a that classiest statement, that classiest statement, it becomes false there, because two sources are needed in order to get the output. Are you getting it? So that's why using this one, we can have this temperature. So we can find out the temperature of the source, which is equal to arbitrary constant that he has derived it, and he has got around 273.16. There, some value of heat transfer will be there. And that. So in Carnot cycle, we have studied. It comprises of 4 processes. One is 2 isothermal process. So and 2 adiabatic process. All are reversible. So if you draw this one, maybe diagram of this, 2 isothermal process, let us say these are the 2 isothermal, and this is adiabatic. So 1 to 2, heat addition will be there, and 3 to 2 to 3 is an expansion. So work done. 3 to 4 is a rejection of heat, Q2, and this is an adiabatic compression process. So the cycles, what you learned, the 2 sources, if it is there, this is maintained at temperature T1, and this is the source, and here is the sink. It is maintained at the temperature T2. If Q1 is the heat transfer from this, right? So as a work output will be there. It's a rejection is Q2. So the efficiency of a Carnot cycle, we can write it as the output by the input. Output is nothing but W upon the input is Q1. So output is again it is Q2 minus Q1 upon Q1. Okay. So heat supplied, sorry, here it should be, because Q1 is more than Q2. So it will be here Q1 minus Q2. Q1 minus Q2 is nothing but W, and heat supplied is Q1. So what you will get it, this thing, So efficiency is equal to 1 minus Q2 upon Q1. And it is also proved that this efficiency, not only it depends upon the temperature, that is T2 upon T1, because Q2 is proportional to T2 and Q1 is proportional to T1. So since it is a reversible process, so any abstraction, we are thinking that any taking heat from the source T1 will not alter. And similarly, we are thinking that any addition of heat into the sink will not alter the temperature T2. If in that case, so for an isothermal, it is a constant to adiabatic and isothermal process. So it does not depend upon Q2 and Q1. That is, it does not depend upon the mass or the fluid flow. So it depends upon the target temperatures T1 maintained at the source and T2 maintained at the sink. So this concept will help with the Kelvin Planck statement and with a series of that thing. So it is helpful to formulate the relation between the Kelvin temperature and degree Celsius temperature, as I said. Okay, so now without wasting more time here, just we have discussed what is Clausius theory. So this is a Carnot theorem. Carnot cycle is there, Carnot engine. So now in the Clausius inequality, I think you have studied this equation. Any cycle you take, this assume that this is a reversible, original reversible cycle. Okay. So if this cycle is divided into number of adiabatic, reversible adiabatic process. So these are reversible adiabatic process. 1, 2, 3, 4, 5, 6. You just divide with the reversible adiabatic process, and in between that you just put the isothermal process, the reversible isothermal process at the top as well as at the bottom. So now in the Clausius theorem, what we found that the heat absorbed during A to B is equal to heat absorbed during the process from here to this, from this to here, and again to this. So that is at constant adiabatic process and isothermal process. So if you addition of that, we have made it equal. So that's why we can take it equal to any kind of this type of process. What you are seeing is this curve you are seeing, isn't it? So it is replaced by a temperature line. So here just it is replaced by a temperature line. So this curve we can omit it because the heat rejected in this curve is equal to the heat rejected at an isothermal process. So for this you just try to read Clausius theorem. Clausius theorem, if read it, you will come to know this one. And now a series of number of Carnot cycles we have used here. So with this we can find that dq1, as I said that dq1 at temperature T1 is equal to dq2 at the temperature T2 is equal to dq3 at the temperature T3 and is dq4 at the temperature T4. For a reversible cycle, it's all equal to 0. So that's why it does not depend upon the path followed. So hence this becomes a property. So dq by t, the heat transfer per unit temperature, it becomes a property of a system. So hence it is a point function or a state function. It does not depend upon whether it is followed by this curve or this curve. So we are knowing that this is it. It is only the temperature, because in the Carnot cycle we have proved that the Carnot efficiency is 1 minus Q2 by Q1, or it is 1 minus T2 upon T1, because finally it depends upon the temperatures, right? So with this, we can say that this for a this dq by t, that is nothing but an entropy. If S2 is the difference of temperature, entropy at S2 minus S21, so then it is dq2 upon T2 minus dq1 upon T1. So this is nothing but the entropy, that is ds is equal to S2 minus S1. Okay, so that is dq upon t. So this is equal to 0 for a reversible process. Is greater than 0 for irreversible process. These things you try to go through the book and try to get what is the irreversible. For always, for an irreversible process, entropy will be always increasing. Entropy is always more, and for a reversible process it may be equal to 0 or less than 0. And for an that is if it is a spontaneous and irreversible process, for that system always the entropy is increases. Entropy per unit Kelvin, if you take it as a property, but if you take it, if you multiply with the mass and all, that becomes at entropy. It's an energy it accumulates in the universe, because whatever the process we are carrying it out, all are irreversible. Ideally, we are saying it's all we are taking reversible, but actually they are all irreversible. Since the thing is that the process what we are using all are irreversible process, hence there is an accumulation of this spontaneous, that energy it is there, that entropy energy. It will be stored in the universe, right? I think this is a very interesting phenomena. So once you have to go in deeper in that, you try to understand what is entropy. So entropy is a thing. It is born from with the second law of thermodynamics. Okay. So try to understand what is entropy. So next, we will go for the slides here. Just I will put down that slide. So already we have learned this one. This is okay, this is entropy of the second law of thermodynamics, as I said in the last class. So surrounding, if the heat rejection is there, so the entropy of the surrounding will definitely increase. And if it is a system, if it heat takes, so that entropy of that thing will increase, whereas the surrounding system will decrease. Okay. So this is the entropy of a gas. S2 minus S1 is equal to dq upon T, or ds is equal to dq upon T, and dq is also equal to dH minus VdQ. Just in the last class itself I have proved this one. Okay. Where Cp is the capacity of the gas, and substituting these values, dH is equal to Cp into dt, and Pv is equal to RT here, and putting what is V is equal to RT by P, and then integrating this equation, we can get this equation. S2 minus S1 is equal to Cp into log base to E. In means log base to E, T2 upon T1, and this is R into P2 upon P1. So this you try to remember this equation. Anyway, the derivation will not be there for you people for the diploma, but if you want to calculate, so for the calculation part it is necessary. This is in case of even that is refrigeration and air conditioning also it is necessary. So try to read this equation and remember this equation. Okay. So in the next class, I will take what are the reversible processes. So and then we will go for the air cycles or Otto cycles. Thank you.